This beautiful boat is the Faley. It's a steel-hulled sailing ketch. It was built in 1923 and for years acted as a workboat around the coast of South Australia. Now it does educational trips with schools, pleasure trips, all sorts of things. You can come on it yourself if you want to. And it does give you a good idea of what it was like to work on a sailing ship hundreds of years ago when they first came out to Australia. And there were many risks. Australia has more than its share of shipwrecks, because a ship like this, driven by the wind, could get into trouble in uncharted waters and run aground. With only the wind to blow it about, it couldn't always get off. So one of the essential bits of equipment that the captain relied on was this. It was the sounding lead. It was very important. These days you can tell how much water there is under the boat by using the echo sounder, but in those days you didn't have one. You had to rely on this. And to throw it, you actually heaved this large lump of lead out to the front of the ship. Now attached to this big lead weight is this. It's a long rope and it's got some very distinctive markings on it. They told you how deep the ocean was. Let me show you. The first sign was that. Bit of leather cut into two. That meant 2 fathoms. 1 fathom on, or about 2 meters, you found the 3 fathom mark. Again, a piece of leather with 3 tags. Then that one meant 5 fathoms, 7 fathoms, and the piece of leather with a hole meant 10 fathoms. Well, this is how it was done, more or less, literally by heaving the lead. Well, the fellow who was doing this job could, as he read the depth, call it out to the captain. And he called it out in 2 ways, by the mark or by the deep. See, if this one was just showing at the waterline, that was an actual mark that told you how deep it was. He'd call out, by the mark, 7 fathoms. But if this one, the 10 fathom mark, had just gone under, that was by the deep. He'd estimate how much more there was, perhaps another fathom, and call out, by the deep, 11 fathoms. So the captain then could tell how much water there was under the ship. Now he might have needed that because he was coming into anchor, and you needed a good surface to dig your anchor into. Hard rock is no good at all, sand's not bad, and gravel maybe. So in the end of the weight was a lump of wax. It was sticky wax, and embedded in that would be a sample of the sea's bottom. As you can see, embedded in this is a lump of gravel. So we now know that under it is, say, 11 fathoms, and there's a gravelly shoal. And that was very important for the captain to know.
So Keith, what actually is in this box?
Well, this is an 18th century astronomical quadrant, a very beautiful piece of equipment, a nice instrument, and in pieces it's possibly associated with someone you will know very well, however, and that would be James Cook.
James Cook? I know him.
Yep. So let's maybe take a look and see what we can find.
Okay, let's do it. Oh, look at that, it's even wrapped like a Christmas present. 12-inch Astron quadrant by Bird, 15 parts, each numbered, 12 parts in box.
This would have been made in the 1760s and used for the expeditions associated with the transit of Venus, which of course you know very well. The Royal Society bought lots of instruments to lend out to astronomers who were going off to make observations. Cook's expedition was part of that. They were very bad at recording which instruments went to who. So it's always just that there's always a little bit of doubt in our minds as to which instrument is associated with which person. So possibly Cook. There are some interesting elements which might suggest that a little more strongly, but we'll need to unpack it to find out. They were very bad at recording which instruments went to who. They were very bad at recording which instruments went to who. So it's always just that there's always a little bit of doubt in our minds as to which instrument is associated with which person.
To illustrate how he did the experiment, I'm going to do a very simple-minded demonstration of how you would do it. Here is my bob. It should be a spherical thing, but I can't be bothered to find one, or George couldn't find one, and George is wonderful, so I don't want to be rude about him. Then I'm going to fix it with a bit of string and support it from a suspension there. The thing is, if I were to let this go and give it a little jitter, it would go round in an oval path, and I want to avoid that. So the trick is, as used by Monsieur Foucault, Léon Foucault, is to put a bit of string there. I'm going to set fire to this. There's still some vibration there, but I would leave it to go, and then suddenly it goes, and then you get it going in a plane. The reason I used fire was if I used a pair of scissors, I'd jog the bit of string. If I do it with a flame, it cuts through and there's no jittery motion either way, so you get it going in a plane. Now, somebody did this experiment at the South Pole, a man called Alan Baker. And he tried to set it up. He had 30 meters of wire, everything was perfect. Only there's the Treaty of the Antarctic, which forbids the use of flames, so he couldn't use this trick, and he spent ages trying to get it to go right, but eventually he managed to get it more or less perfect and found that it actually goes round in 24 hours plus or minus something at the South Pole. It goes round the opposite way in the southern hemisphere compared to the northern hemisphere. There's one thing that goes wrong with this experiment. As you can see, the amplitude of this oscillation changes with time. it decreases because of the friction of the air. And you make the system bigger and there's still friction of the air. So this guy found that at the South Pole, after about a couple of hours, it died away too much. So he had to do his measurements in about 20 minutes. If you make the thing much longer and put it in a museum like the Pantheon, you will find that it still decays in a couple of hours, 4 or 5 maybe. So either you set it running for a certain length of time and see that it will rotate for a certain angle, and then have a big fanfare and start it again and burn it with another bit of match, or you put a little motor in the top and give it a little jiggle and put energy in at the top, which is somehow cheating because you're actually pushing the damn thing, and you have to make sure you push it in a way which is not going to cause a torque. So that's the way it's done in a lot of museums.